So when I give a physics lecture, it's interesting. We love the physics lectures where we have the ability to demonstrate all the physics we know. And you've already gotten that this morning. Sound, light, maybe not water, and a lot of electricity, computing, screens. I'm going to talk about gravity a little bit and try to aim it at this themes of this meeting, more or less to illustrate what physics is and how we move forward in physics within the concept maybe of how it all began is what I'll try to get to by the end. But one of the things that I think this section is what's the point? For physics, that's simple, doing the kind of physics I do. It's much more complex for most of this meeting, but for physics, it's simple. We just try to satisfy our curiosity. As kids, curiosity is what drives us. And when we get to be adults, most of us do other things. Some of us still act like kids and try to satisfy our curiosity. So everything I do has to do with curiosity. Remember, the curiosity killed the cat. Anyway, this picture here is a picture of the Big Bang, and I'm going to come to that at the end because we have a television program called The Big Bang. We talk a lot about the Big Bang, but we don't understand it, and I'm going to try to give a hint why that's a burning question, at least for me, and how we might get at it. But I'll do that through talking about the studies of gravity first that I've done. So the story, human story at least, starts with Einstein. In 1915, Einstein made a new theory of gravity. We all grew up learning gravity through Sir Isaac Newton, who had a theory of gravity, which he called unified gravity. It described how the apple falls out of the tree to the earth. It described how the moon goes around the earth. It described how the earth goes around the sun. It described the tides. Described everything to do with gravity basically for more than 200 years and was the most successful physics theory ever. He also introduced the scientific method, so Newton was pretty important. Einstein came along, and in 1915 he made a new theory of gravity. So why did we need a new theory of gravity at all since we had a theory? It's a little bit the way physics works. We have a theory. There was nothing wrong with Newton's theory. It just didn't do the job. I'm not going to talk about this complicated formula, by the way. You learned a formula that was much simpler, that was Newton's formula. But Einstein came along and made a new theory of gravity. It's really complex and hard to understand, even for physicists. But it solves two problems that Newton had. Newton's theory that we all learned told us that when the apple falls out of the tree, the earth pulls it down. Or our teacher told us if we jump up, the earth pulls us down. And some of you, not me, might have asked your teacher why the earth pulls you down. Newton never explained that. Einstein does. So Einstein attacked the unanswered part of the question. What makes you attracted to the earth? What makes two bodies pull together? I'm not going to explain it. It's the warpage of space-time, these words that you hear, which are explained by this formula here. The second problem with Newton's theory, and the fancy physics words are instantaneous action at a distance. What does that mean? That means when the apple falls, you see it right away. Or if the sun were to burn out right now, it takes 7 seconds for the light to get here, but you would know it from gravity immediately in Newton's theory. In Einstein's theory, the message comes at the same speed as light, the speed of light. So he solved those two questions. And then he introduced the possibility that there was something new. The first thing that was new is that light would curve. And there was a spectacular experiment done by looking at stars going behind the sun in 1919 and measured this curving of light around the sun. The reason it bends going around the sun is this warpage of space right around the sun that causes the turn. The second prediction of Einstein, and it shows that burning questions might take us a long time, was in 1916, I think I have it. No. In 1916, he predicted there was something called gravitational waves. That's waves, just like electromagnetic waves that made all the light and sound and so forth you just heard. And 100 years later, so it takes us a while, we saw gravitational waves. We saw them from something called black holes. A black hole, I'm not going to describe mathematically, it's a difficult mathematical concept. But conceptually, what it is a region of space that has so much gravity that nothing can get out. Not even light, because light bends, remember. So everything is trapped, therefore it's black. So this is a black hole. They come about from a star, a heavy star that collapses after it burns up all its fuel and makes a final, very dense amount of matter. Our sun is too small to do that, but a heavier star can make a black hole. So we saw two black holes that are going around each other, just like the moon around the Earth, going around each other. But by Einstein's theory, as they go around each other, they accelerate and lose a little bit of energy. That goes into gravitational waves. And eventually, because they lost energy, they spiral into each other. I'll show you that in just a minute. But first, the distances. So here's a picture of Pueblo City and Mexico City. And here's the two black holes that we observed put on top of that. One of them is 36 times the mass of our sun. The other one is 29 times the mass of our sun. And they're only apart about the distance between Puebla and Mexico City. And they're going around each other at half the speed of light. That's what we observed. Each of these, by the way, to put it in reference, the black dots are 10 million times the mass of the Earth concentrated into this small space. So that's what makes it have such strong gravity. This is the recreation of the observation that we made 100 years after Einstein predicted of the merger of two black holes. They're going around each other. They're losing, from way out in the universe, they're losing energy and they come together. You'll note at the top, I say 1.3 billion years ago. That's how far away this was in the universe, and it was traveling all this time. By the time it got to us, we could detect it. This is then the gravitational waves going out, and they cause, and that's what we detect, that space gets warped. Whatever it goes through or comes to gets warped. So here it comes toward the Earth, takes 1.3 billion years, and by the time it gets there, it warps the Earth. The amount, I exaggerated a little bit in this picture, as you'll see. So it doesn't quite do that. We're not able to measure it. It's much, much smaller. And we needed a special instrument to measure it, and that's what took so long. And the special instrument is shown here, which I won't talk about in detail because it's not the point today. These are the two instruments. They're large. They're 2.5 miles on a side. One of them in the state of Louisiana, the other in the state of Washington. Anyway, that was the observation of gravitational waves. This is the signal. I'm not going to explain the signal, but it's basically getting bigger. And that's as the waves merge. This is about 0.2 of a second when we observed it. These are the two different laboratories, and they saw exactly the same thing, separated by 7 milliseconds, which told us where it was coming from. So that was the discovery. I went just a couple days ago before coming here to consult with Mr. Einstein in Bern, Switzerland, where I flew directly from there with a night's sleep here to ask him what I should talk about. And after, as a result of this, in terms of the burning questions, we disagreed, so we didn't do that. So instead, I'll talk about what I think is a burning question as we go on. So first, to illustrate why science as it develops gives you the ability to do something else. So we did something, we got awarded for it, but this gives us the ability to move another step somewhere. This is very much in the case of gravitational waves like Galileo in 1608. He looked through a telescope in 1608 for the first time. They made lenses for glasses. He looked through a telescope, he looked at Jupiter, he saw Jupiter had 4 moons. That told us a lot about the fact that planets go around something central like the sun, so it had a lot of implications. And it was the beginning of astronomy, the first time that anybody looked at the sky with something other than our eyes. And astronomy's gone a long way since then. We now, for the first time, have looked at the sky through gravity instead of through light or electromagnetic waves. And again, there's many opportunities for what can be done. So the question is, what can you do? We already did something in the last year, and that's shown here. There's another